Hi everyone, in this module we are going to talk about algorithms involving number theory problems. And number theory is an important topic when it comes to competitive programming. So we will see we have multiple sections on number theory, and in this section we are going to talk about problems which are related with prime numbers. Okay, so just for a recap, what is a prime number? A prime number is a number which has only two divisors, the number itself and 1. Okay, for example, if I talk about the number 7, it has only two divisors, 1 and 7. Talk about number 11, 11 has only two divisors, 1 and 11. Talk about number 2, it has only two divisors, 1 and 2. So all of these numbers are examples of prime numbers. Okay, so what are examples of non-prime numbers? Let's talk about number 9. Okay, so 9 is having 1, 3 and 9 as its divisors. What about number 6? So it has 1, 2, 3 and 6. So all of these numbers, they are not prime. Okay, so these are examples of not prime, whereas 2, 7, 11, 5, they're examples of primes. So many times you will find questions revolving around computation of prime numbers. Okay, so the most basic question could be, given a number, you want to check if it is a prime number or not. Okay, so check if a number is prime or not. So there are multiple ways of checking it. So the most basic way of checking if a number is prime or not is, for example, if you have something like, let's say 7. Okay, and what you will do, you will try to find divisors in the range 2 to n minus 1. Okay, so divisors in the range 2 to n minus 1. So if you see, if one of the numbers in this range is able to divide 7, then it is not a prime number. So 7, I will check divisibility with 2, 3, 4, 5 and 6. Okay, because we discussed prime number has only two divisors, 1 and the number itself. So if you find at least one divisor, okay, if you find at least one divisor in the range 2 to n minus 1, then you can simply say this number is not prime. Okay, otherwise you can say this number is prime. For example, about the number 9, you will easily find a divisor 3. Okay, so and this lies in the range 2 to 8. So we can say 9 is divisible by 3, hence 9 is not prime. So the complexity of this method of checking whether this number is prime or not, so we can say this is roughly taking order of n time. Okay, it's roughly linear. Okay, or it is exactly linear, right? Now what you can do is, if you have a different number, okay, or if you want to do it for a large number, then it will take a lot of time. Okay, so n grows if lot of time to check if a number is prime or not. So if n grows, the time will also increase linearly. That's what we are trying to say. So is there a better way to check if a number is prime or not? Yes, there is. So that method we call as the square root method. Okay, so for this we need to understand a property that instead of iterating from 2 to n minus 1, okay, let's say this is 2, instead of going till n minus 1, we can go till root of n. Okay, we can go till root of n. So there are some people who say, okay, we will check till n by 2. So that is also fine, but root n is even smaller than n by 2. Okay, so basically instead of running till n minus 1, you can run till n, run your loop till root n only. Now you may ask why this is true. Let us take an example of a number, let's say 36, and let me try to write the divisors of 36. So 36 has divisors like 1 and 36. Okay, we will not talk about these divisors. It has divisors like 2 and 18. Okay, so 2 into 18 is 36. We have 3 and we have 12. 3 into 12 is 36. We also have 4 and 9. 4 into 9 is 36. And we also have 6. Okay, 6 into 6 is 36. So you can see there are so many divisors of 36. So now what happens is, I'm not writing 6 again, okay, because it's a perfect square. But the thing that we are discussing is also true for non-perfect squares, okay. So most of the times what happens is these divisors occur in pairs. So basically you are saying a into b is what? A into b is this number 36. And what we can observe is that these divisors occur in pairs. So with 2 you can have 18, with 3 you can have 12, with 4 you have 9, with 6 you have 6 itself. Now, and with 1 you have 36, that we are not looking for right now, okay. 1 into 36 is also 36, but we are not worried about these divisors, okay. We need the divisors in the range 2 to n minus 1. So basically some people say the largest divisor would be n by 2. That's why you just need to check till n by 2, which is fine, okay. You can do a check till n by 2. That would require how many iterations? Roughly n by 2 iterations, okay. Okay, and if you check till n minus 1, it will require almost n iterations, okay. But I'm saying instead of doing n by 2 or n iterations, you can also do in root n iterations. I'm going to explain you the reason why, okay. Let's talk about the reason why. So if you look at the divisors of any number, so you will find that if this number is, let's say, so this number is what? Root n, okay. So there are some divisors, okay. We have root n into root n, that is equal to 36. So what I'm saying is, if you try to increase the value of this number, okay, let's say you have a divisor which is greater than root n, okay. If there is a divisor which is greater than the value of root n, then there must be at least one divisor which is less than root n, okay. So if you try to increase the value of this number, let's say you make it, let's say 9. So you say 9 is a divisor. So there must be a divisor which would be less than equal to root n, okay. So then there must be a divisor. So if there is a divisor, then if there is a divisor which is greater than root n, then there must be a divisor which is less than root n, okay, which is less than root n. So effectively what we are saying is, a higher divisor of a number cannot exist without a smaller divisor. So it is enough to check there is if a number is not prime, if there is at least one divisor in the range 2 to root n. That's what we are trying to conclude, okay. Now what you can do is, you can reduce the complexity of checking if a number is prime or not from order of n to order of root n, if you follow this approach, okay. That means yes, it is true. And what you would be doing is, let's say if n is 10,000, okay, something like this, then it will just take 100 iterations to check if a number is prime or not. That means root of this number is just 100. So you can see this is actually going to be very fast. In one case you are doing 10,000 iterations, in another case you're just doing 100 iterations. So this is effectively reduce the complexity a lot, okay. But there are other ways also. Now suppose you want to find all the numbers which are prime in the range, let's say starting from 0 till 10 power 6, okay. Let's say this is what n is. If you follow this approach, if you follow the first approach where you check every number is prime or not, so you will spend easily, so you need to iterate over all the numbers, that is order of n, into to check if a number is prime or not, it will take order of n square time. If you follow the root n method, that is the second approach, you can reduce down the complexity to from, you will still need to iterate over all the numbers from order n into to check the number is prime or not, that is n into root n. Still it's not that efficient. So we also have one more method which is known as prime sieve, okay. So what we are going to do, we want to compute primes in a large range, and we are going to do it in order of n into log of n time, okay. So this is what we are going to see next, how to use a prime sieve to compute primes in a large range, okay. So that's a quick introduction of what are prime numbers, how to prime numbers. And the first two methods are pretty easy. You can do it yourself. And now we are going to look at prime sieve from the next lecture. Okay. So that's all. See you in the next video. Hi everyone. In this lecture, we will talk about the concept of a prime sieve, which is also known as sieve of Eratosthenes. As I discussed, it's a popular technique of finding out prime numbers, and especially it is helpful when you want to pre-compute a lot of primes. Okay, so what you are going to do is we'll start with a array. Okay, and let me just draw a big array, and right now I'm just assuming it has the numbers from 1 to 20, but it could be a larger range as well. Okay, it starts from, let's say, 1 and it goes till a certain index, let's say n. Okay, and n could be a large number such as 10 power 6 or 10 power 7, something like that. So what we are going to do, we are going to first write down all the numbers, like let me just create some slots, and then we'll put the numbers into this. Okay, let's say we have numbers from 1, then 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and let's say 19, and let's say one more 20. Okay, so now what this algorithm does is it picks a number from the array. Okay, and we'll start from 2, and we will mark all multiples of 2 as not prime. So we know that 4 is not prime. Okay, so we say 4 goes off, 6 is not prime, 8 is not prime, 10 is not prime, 12 is not prime, 14 is not prime, 16 is not prime, 18 is not prime, 20 is not prime. Okay, so what we do, so we say, okay, 2 is a prime number. Okay, so in the primes output we can say, okay, 2 is a prime number. And what we did, we marked all multiples. Okay, so 1 is a special case. We'll mark 1 and 0 as not prime by default. Okay, 1 and 0 are not prime, so we start from 2. We mark all multiples of 2 as not prime. Okay, next time we move to the next index. Okay, which is again, which would be a not prime number, which would be a prime number. Okay, we move to 3 and we mark all multiples of 3 as not prime. Okay, so what we do, let me just choose a different color. Let me choose this color. So let me mark the multiple of 3. So one multiple of 3 is 6. It is already marked what? It is marked not prime. So we mark 9 as not prime. 12 is already marked. So we mark 15 as not prime. 18 is already marked, and then the next number would be 21 or so on. Okay, so 3, 6, 9, 12, 15, 18, and so on. Okay, what we do next, we say, okay, since no one marked 3 and we have already reached 3, then 3 is a prime number, so we add 3 to the list of primes. Next time we go to the next number, and let's say that number is what? That number is what? That number is 5. And since no one marked 5, okay, we have, oh sorry, we go to 4, but 4 is what? 4 is already marked as what? 4 is marked as a not prime number, so we just skip it. We don't do any work at 4. Okay, so 4 will not be included in the list of prime. So we go to 5, and we have already seen the numbers from 1 to 4. That means and 5 is not marked by any of these numbers. That means 5 is a prime number because we have already iterated till n minus 1. Okay, so we say 5 is what? 5 is a 5 is a prime number because there is no divisor in the range 2 to n minus 1. We mark multiples of 5 as not prime. So we have a multiple which is 10, it is already marked. We have a multiple 15, it is already marked, and we have now 20, which is already marked. The first multiple that we will get that is not marked will be 25. Okay, so we mark multiples of 3 as not prime, we mark multiples of 5 as not prime, and so on. Next, what we go to number 7. Okay, and we will do the same step again and again. Okay, we'll go to 11, we'll go to 13 and so on. But what you now can see is the numbers which are left now, they are only the prime numbers which are getting left. Okay, so we go to 7, so we include 7, we mark multiples of 7. Then we go to 11, okay, because it's not marked, so it is a prime number. Then we go to the next number that is not marked, that is 13, we mark multiples of 13. Okay, then we go to what, 17. Okay, and then we see, okay, the number is 19. So what you can see is, if you keep on doing this process, you would be only left with primes in your input array. Okay, so in this array only prime numbers are left, rest everything is going to get cancelled. Okay, so basically at any number p, okay, so what this algorithm is saying, we are saying at any number p, we mark the multiples of that number p as non-prime. Okay, and this p must be a prime number because it is not marked. Okay, so let me just write it down. So we mark the multiples. So what are the multiples? So the first multiple is what? If the number is p, the first multiple would be what? 2p. Okay, then it would be like 3p, then it would be 4p, 5p, and so on. Okay, so effectively for 5 the multiples are what? 10, 15, 20, 25, 30, and so on. But now there is one more optimization that we can do. Okay, let me talk about an optimization that we can do. Optimization. So what we looked at is, when we talk about 5 or any other number p, okay, let's say this number is p, we saw that the first multiple that would be unmarked, it would be nothing but 25. 25 would be the first number that would be marked as not prime by 5. So what I'm trying to say is, instead of starting a loop like this, so you can say, okay, for a number j that is equal to p, you say j less than equal to the range n, you can say j equal to that number j plus p. You're starting from a number what, and you're saying, okay, mark this number j as not prime, sorry, j equal to 2p. Starting from this number 2p till the range n, you mark all the multiples as not prime. Okay, but what I'm saying is, instead of starting from 2p, you can actually start from p square. Okay, you can actually start from p square, and you can mark all the numbers in the range p square to n as not prime. Okay, that will actually save your work, that will actually save some work of iterating over these numbers. Now you may ask how this optimization is possible. So let us go back to a concept that we have discussed already. So what this concept is, let's say if we have a number n, okay, and for this number we already discussed that there would be at least, if this number is what, if this number is non-prime, then there must be at least one divisor which is less than equal to root n. Okay, let's say if this number is p, then this number must be what, let's say if this number is p, then this must be p square. Okay, if I just write the other way around, okay, if let me use a different color for this one. Okay, or I can say if this number is like p, then it must be p square. So what I'm saying is, for a number n, okay, we have already iterated till this number. Okay, for all the numbers which are in this range, let's say which is less than n. Okay, so if n has divisor that is up to root n, okay, the smaller divisor of n is up to root n, then for all the numbers which are less than equal to n minus 1, they must have a divisor in this range. They must have a divisor in this range if they are not prime. Okay, if they are not prime. For example, if I talk about the number 25, So if 25 has at least, if 25 is not prime, then it must have a divisor up to 5. And for the numbers 24, there must up to 24, there must be a divisor in the range p minus 1, okay, from 0 to p minus 1, if it is again not prime. So that's the idea. So effectively what I'm saying is, if you have already uh, if you have already marked the multiples of the numbers which are in the range 0 to p minus 1 as not prime, and let's say this number is p, then what I can say is, up to this number 24, up to the number 24, all the non-primes would have been marked by the numbers in the range 0 to p minus 1, and hence for 5 or for any number p, you can directly start marking the numbers as not prime from p square till n. Okay, so this is another optimization. Okay, so although this loop is correct, but instead of starting from 2p, what we can say, start from p square. Okay, so that's the optimization that we would be doing in our code, and it will help us to reduce some work. Okay, so I hope you understood the algorithm. Okay, and if the optimization part is little not clear, we will do it again in the coding video. And if you want to see a visualization for a larger example, here it is. So what we did, we picked 2 and we are marking all multiples of 2 in red as not prime. Then we picked 3, and since 3 was not marked, so we mark all multiples of 3 as not prime. Then we pick 7, 5, 7, and so on. Okay, and here you can see the numbers which are left unmarked, they are the prime numbers. Okay, so that's all about the logic of this prime sieve. In the next video we will discuss the implementation along with one more optimization that we will do while writing code. Okay, hi everyone, so in this lecture we are going to write the code for prime sieve. So let's begin. First of all, what we are going to do, I'm defined a constant macro that n is defined as 10 power 6, and what we are going to do, we are going to write a function that will compute the prime sieve for us. Okay, so maybe I can say vector of int, let me call it as primes, and everything is, let's say, initialized with value 1. That means I'm using the fill constructor, so this vector contains 10 power 6 entries and everything is 1. Okay, and now I can say void prime sieve, I can pass the vector of int by reference, and what we are going to do is we are going to iterate over all the numbers from 2 to n. Okay, so for int I equal to 2, I less than equal to n, I plus plus. Okay, so, or let me just call it as sieve would be a better name for this one. Okay, and here what I'm going to do is I can say let's pick a number I. Okay, let's pick a number I. So first of all, I can say p of 1 and p of sieve of 1 and sieve of 0. I'm going to set them as 0. Okay, so 1 basically means everything is prime in the beginning, so I say okay, mark 1 and 0 as not prime. Then I can say okay, start from 2 and mark all multiples of ith number as not prime, and this ith number must be prime. Okay, so ith number which is prime as not prime. So effectively what I say, okay, for some int j, okay, I can say if, so first of all let me put a if condition. If this number, if sieve of I, if this is 1, that means only then I will mark the multiples of this number as not prime. So effectively I can say int p is what, sieve of I, if this p is prime. Okay, so if p is 1, that means I can start from what, I can start from, sorry, not sieve of I, but yeah, I can write it like this. Yes, for int j, that is equal to what, that is equal to I into I okay, and I can say j less than equal to n, and I can say j equal to j plus I. Okay, so this statement is actually not needed. I can just check if sieve of I, if the ith number is not marked, then it is a prime number, and we'll mark all multiples of that number as what? We can say sieve of j should be equal to 0. Now one thing may happen is, now this I could be a large number, and let's say I is 10 power 5, then you're multiplying two numbers which are in a long range. Okay, so although we are checking j is less than n, but the value of j will not be computed correctly, so effectively we should use a long here. Okay, that is a possible mistake that people can do, and it's also good to make I as long as well. Okay, so I can say hash define ll as long, so instead of saying int I can say lli. I can call this as llj. That seems correct, and yes, it should work fine. So that's the complete logic for computing the prime sieve. Now you may ask, what is this condition? So let me just tell you what I did. Let's assume that the value of I is, let's say, 5. Okay, then for 5 I'm saying what are the multiples that we are computing. So for 5 you can go to 10, 15, 20, 25, 30, up to whatever is the last multiple of n up to 10 per 6, that is this one only. Okay, yeah, 10 per 6, that is n. Okay, so I'm saying, okay, for 5 I can directly start from the multiple 25, that is what, that is I square. Okay, that means j starts from I square, and I want to go to the next multiple. So how do you get 30 from this? I say, okay, I square plus I, then again if you add a I, that means I square plus 2I. Okay, then I square plus 3I. So this is what this increment condition is doing, and this initial increment is the part of the optimization, the initial. Okay, so instead of saying j equals to 2I, I said j equals to I square, because of the same reason that we have discussed in the previous video. For example, if you talk about the numbers in the range, let's say 5 and 25, the first multiple of 5 that will not be that would be marked would be 25. All other numbers which are less than 25, like talk about 24 or talk about 23 or talk about 22. Okay, so 23 is a prime, it will not be marked, it will stay as it is. But about 24, you will find at least one divisor in the range 0 to 5 minus 1. Okay, or 1 to 5 minus 1. Okay, so there must be at least one divisor. So we will not talk about 0 and 1 as divisors. So effectively in the range 2 to n minus 1, there would be at least one divisor of 24. In the range 0 to n minus 1, there must be at least one divisor of 22, 21, okay, 20, even 15. Okay, why so? Because of the root n property that we have already seen. So for this number p, or for this number I, we are starting marking the numbers from I square. The next number would be 30, that is I square plus I. That is what we are computing in j, and we are saying sieve of j is 0. Mark all the numbers as not prime. So this is saying marking j as not prime. So all right, so this sounds good to us. Now suppose if I want to print, I want to see what all prime numbers we have computed. So maybe I can just do it in the range 0 to 100 I plus plus, and I can check if sieve of I is 1. I'll just print out that number just to check if I'm making the sieve correctly or not. Okay, so here we are creating this sieve, and we should call the method prime sieve, and we should give the sieve, and this is passed by reference. Okay, that means the changes should be reflected. So we need to include vector. We are done, and let me just run this code, and you can see we are getting all the prime numbers correctly in the range 0 to 100. Okay, so although we are doing it for 10 power 6, but we are printing only till 100. Okay, you can print till 1000 also, that will also work. Okay, and you can print till 10 per 6 also, but we can't check. Okay, we can't check. So yes, now one more optimization that we can do is we can say start from 2 and mark all multiples as. We can also start from 3 and we can mark all multiples of 2 as not prime. Okay, I think this should be okay. This is fine. Okay, so one more optimization that people generally do is they say, okay, mark all, do not iterate over the multiples of 2. Okay, do not iterate over multiples of 2. That would require us setting everything as 1 in the beginning. So here we are setting everything as 1, so maybe we can set everything as 0, so everything is not prime. So initially you can say I will just mark all odd numbers as prime. Okay, all odd numbers as prime. So I can say for int I equal to 3, I less than equal to n, I plus equal to 2, I can say sieve of I as 1. So what we have just done is, so we assume that all multiples of 2 are not prime. Okay, so we set everything as 0 in the beginning, then we set all odd numbers as 1, and then from those odd numbers we say, so this is, let's say 1 2 3 4 5 6 7 8 9 10. Okay, we just do the work for all only the odd numbers. So from I equal to 3 and the same process starts. So we mark multiples of 3, that is 6, 9, and so on, okay, as not prime. Effectively it does not make a lot of difference, to be honest, and you are going to get the same answer even if you do this thing. Okay, so you mark all odd as prime, initialize, okay, and then you say, okay, mark all multiples as not prime. This is also fine. You might see this optimization in some codes. Both the methods are correct. So the method is effectively same, and we are just doing some additional check that, okay, I will say all even numbers, I will not go to the multiples of 2. Okay, so effectively the second method is saying we will not mark multiples of 2 because even numbers can never be prime. That's the what second method is doing. Okay, so I hope you understood how to build the prime sieve, and that's all for this video. Hi, so in this lecture we are going to discuss this problem, prime queries. So in this question we are given q number of queries, and in each query we are given two integers. Okay, and these two integers are, let's say, a and b. What we need is we need to find out the number of primes in the range a to b. So both a and b are included. So let me just tell you, we need to find the number of primes in the range a to b. For example, if the range is 1 to 10, the number of primes is 4. The primes are nothing but 2, 3, 5 and 7. Between 11 and 20, again it's a range, the number of primes is 4. That is 11, 13, 17 and 19. We have 4 primes in this range. Now these ranges may be overlapping, so maybe you have another query between, let's say, 5 and 30. So we can see some part is getting overlapped with this query. Okay, so instead of iterating over every range every time and finding out how many primes are in this range, we will solve this problem smartly. Okay, we have multiple queries, and that means a lot of queries can have overlapping ranges, and what we can do is we can pre-compute all the primes once. Okay, we can do pre-compute all the primes once, and you can see a and b are of the order 10 power 6, so we will compute all the primes up to range 10 power 6. Okay, so if you do it for every query, it is going to take a lot of time. Now suppose you have pre-computed all the primes, and now what you can do, okay, you have your sieve ready. that basically tells us, okay, these are the numbers which are the prime numbers. So you have 2, you have 3, you have 5, you have 7, you have 11. Okay, so rest everything is marked as false. Okay, so these are the numbers which are left in the sieve after running the prime sieve. Okay, so after you run the prime sieve up to n, and we also talked about the complexity of the prime sieve is n log of n. Okay, which is very small. Okay, now what you need to do, how you can find all the prime numbers in the range from 0 to n. Okay, so the idea here is you will also make another array that will store the cumulative sum, or the cumulative sum of count of primes. Okay, so basically I'm going to say, what is the number of primes that you have up to an index 2? Let me draw an array. Okay, what is the number of primes up to an index 0? 0. What is the number of primes up to index 1? It is 0. What is the number of primes up to index 2? So 2 is a prime number, so I will say, okay, I have only one prime up to 2. What about up to 3? So whatever primes you have till this point, and you will check whether this number is prime. The answer is yes. Plus 1, so you make it, okay, 2. How many primes up to 4? It is 2. How many primes up to 5? It is nothing but 3, because 5 is a prime number. How many primes up to 6? Again 3. Okay, how many primes up to 7? It is going to be 4. So basically I'm saying that cumulative sum of I is nothing but cumulative sum of I minus 1 plus what? Plus 1 if the number I is prime. Okay, how do you know if the number I is prime? By looking at the prime sieve. Okay, by looking at the sieve you can check whether this number is prime or not. Okay, so similarly up to 8 you have 4 primes, up to 9 you have 4 primes, up to 10 you have 4 primes, up to 11 how many primes you will have? You will have 5 primes, because the number 11, that is I, is itself a prime. Okay, now someone asks, okay, tell me the numbers in how many primes I have in the range, let's say 1 to 11. Okay, or maybe yes. So you look at, okay, up to 11 I have for 5 primes, and for 1, since 1 is included, you need to check how many primes up to 0. So there are 0 primes. So between 1 and 11 there are going to be 5 primes. So you're simply doing C sum of 11 minus C sum of 0. That gives you, okay, these are the primes I have. Okay, so for any range A to B, you can simply say the number of count of prime is nothing but C sum of B minus C sum of A minus 1. Okay, because this tells me, okay, how many primes till A minus 1. This tells me how many primes till B. If you want the primes in the range, let's say from 3 to 10. Okay, so up to 10 we have 4 primes. For 3 we will say, okay, C sum of 2, that is 1. We'll subtract 1, so it gives us an answer 3. So we have 3 primes in the range 3 to 10, that are 3, 5 and 7. Okay, so this is how you're going to do the work. Now talking about the prime sieve, it is going to take order of n log of n time. Talking about this cumulative sum array, this also you're going to build only once. Okay, so it is going to take order of n time. And what about each query? So you have q queries. Okay, and those are being done after these two arrays are made. Okay, so it is going to take n log of log n plus the time to build the cumulative sum array, that is how much, that is order of n, plus time for each query. So each query is a order 1 query, so that is going to take q time, and that's it. So you can see this complexity will easily pass the 1 second limit, because n is of the order 10 power 6 and q is also of the order 10 power 6. Okay, and this value would be very small, log of 10 log of 10 power 6, again it would be somewhere less than 5 6. Okay, so it's going to be a very small number, and hence we can say that it would pass the 1 second time limit very easily. So that's all for this lecture. I hope you will try this code by yourself. And now you can solve the problem prime queries. Hi everyone, in this lecture we will talk about prime factorization. And first of all, we need to understand what is factorization. Okay, so given any number, we can break that number in terms of its factors. For example, if I have the number 30, I can write it as 2 into 15. So I say both 2 and 15 are the factors. They are the numbers that divide 30. Or I can write 30 as 2 into 3 into 6. Okay, sorry, into 5. That is also doable. Okay, so what is prime factorization? So prime factorization means breaking a number in terms of its prime factors. So there are many ways to do the factorization, but there is only one way to write the prime factorization. For example, 30 can be written in terms of prime factor like this. So there is only one possible prime factorization for a given number. Okay, so one unique prime factorization we can have. So one unique prime factorization. Okay, and you can see all the factors that we are writing, they are prime numbers. So let's see, how do we actually factorize a number? Let's see. So given a number like 30, so what we do, we follow this division method. We start from 2 and we try to divide 30. So 2 divides 30, so 2 15 is 30. Okay, we again try to divide with 2, but it does not divide, so we go to the next number 3, and we know 3 divides 15, so we say 3 5s are 15. We go to 4, 4 does not divide, we go to 5, 5 1s are 5. So we keep on doing this till we don't get a 1. So we can say 30 can be written as 2 into 3 into 5. Okay, so the way we are doing it is, we are iterating over all the numbers. So we are saying for I equals to 2, okay, I less than equals to n, I plus plus, and I check. Okay, I'm discussing the brute force way. So if n is divisible by I, okay, then what I say while this n is divisible by I, keep on dividing n with that particular I. So n equals to n by I. So let me give you another example. Let's say the number is 72. Okay, so 2 divides 72, so we can write it as 2 into 36. So we will try to reduce 36. So 2 also divides 36, so we write 2 into 2 into 18. 18 is also divisible by 2, we write 2 into 2 into 2 into 9. 9 is also divisible, it's not divisible by 2, so we write it 2 into 2 into 3 into 3. And now what is left is 3, so we write it as 3 into 1. So in prime factorization we don't consider 1. So effectively this is what is the prime factorization of 72. So if you do it using this method, 72, so you say 2 36 are 2 18s are 36, 2 9s are 18, 3 3s are 9, and 3 1s are 3. Okay, so you get the same factorization here as well. So what I need to maintain is with every value I need to maintain a count how many times this 2 is coming. Okay, how many times 2 is dividing, so count is 0, and every time it is divisible, so I can increment the count. Okay, and after this while loop is over, I can print that okay, I is a factor and count is how many times this number is dividing my value of n. So 2 is the count, and how many times? 3 times. Then I get 3 is the prime factor, and how many times? 2 times. Okay, so this is nothing but this is equal to 72. So this is a brute force way of finding out the prime factors. And what would be the time complexity of this approach? So effectively, in the worst case, when let's say n is a prime number, let's say n is 11, this for loop is going to run n times, and this while loop is not going to run in that case, only once. So it is going to run order of n times. Okay, but for other numbers like let's say 36 or 72, you can see this number, uh, the value of n is going to become smaller if you divide it with 2. Okay, so for example, you divide 72, so this is the value of n. So in next iteration it reduces further. Okay, so it is not going to exceed the value n. So this has a worst case when n is a prime number, and this for loop will take order of n time. Okay, in that particular case. Okay, so this is the brute force way, and now we will see some optimizations to this approach in the next video. Hi everyone, so let us see the code for prime factorization, and we have discussed a brute force approach. So what we discussed in that approach is we'll start I from a value 2 and we will go till n, and we will check if the number n is divisible by I. If this is 0, then we'll reduce it. Okay, so we'll remove all powers of, let's say, I. So while n modulus I it is 0, we keep on dividing that number with I. Okay, for example, in a number, if you have multiple powers of 2, for example, the number is 50. Okay, so it can be written as 2 into 5 into 5. So what we do is we say, okay, it is divisible by 2, reduce it to 25. The value of n becomes from n equal to 50 to n equal to 25. We try to divide it with 3, it is not divisible. We try to divide it with 4, it's not divisible. We try to divide it with 5, it is divisible. So we reduce it to 5 and we say, okay, the count of 5 is 1. And we again try to divide it with 5, it becomes 1. So finally we will stop. Okay, this loop will stop. The value of n has now become actually 1. So what we are trying to do here is, so you can see it is actually going to run less than n times. Okay, so in the worst case this loop will run, these two loops together will run n times, but in most cases it is going to run less than n times. So we can say the count of this is 0, and how many times I is dividing, we will increment this count. So we can say count plus plus, and now what we can do is we can print the count here. Okay, we can say, okay, see out, the divisor is what, 2. Okay, and how many times, I, and the power of that is count. Okay, so that will give us one of the prime factors and its power here. And let's try to run this code. So maybe I will take input some n and I will say, okay, factorize this number n. So we have built the code and let's try to run it. So okay, dot slash, if I give the input as 50, I get 2 raised to the power 1 and 5 raised to the power 2, which is correct. If I give 72, I get 2 raised to the power 3 into 3 raised to the power 2, which is also correct. So that means our code is working perfectly fine, and this code takes linear time to run. Now we want to talk about an optimized approach that we will discuss in the next video. Okay. Hi everyone. So let us talk about an optimization to the factorization approach that we have discussed. Let's talk about a number which is, let's say, 99, and we want to do the factorization. Okay, so what we discussed, we will start from the value of I, that is equal to 2. The value of n is 99, and we are also maintaining a count. So count is currently 0, 2 does not divide n, and we go to the next number, that is 3. 3 divides 99, so we reduce it to 33, and we say the count is currently 1. Okay, so we again divide 33 with this current value of I because it is divisible. So we say it is now 3 divides 33. 3 into 11 is 33, and the count of 3 becomes 2. Now 3 does not divide 11, we go to 4. 4 does not divide 11, so the count is 0. We go to 5. 5 does not divide 11, we go to 6. 6 does not divide 11, we go to 7. It does not divide 11, we go to 8. It does not divide 11, we go to 9, and we go to 10. 10 does not divide 11, we go to 11, and 11 divides 11, and the count is 1, and we go to 12. Okay, the value of I becomes 12, and this is the point where our loop stops. Okay, so we exit from this particular loop. So now what happens in this case is, what happens here. So effectively, um, we have spent so many iterations without finding a prime factor. So one observation that we have already learned is, let me just write down the observation. Okay, so the observation is, once n is reduced to a prime number, okay, the only factor of that number will be the number itself. Okay, we have already studied about prime numbers. So prime numbers don't have any other divisors than the number itself. Okay, and one number itself. So at what point we have reduced the number to a prime number? So we have reduced this number. Okay, you can see uh, and let me write another observation. Okay, if a number does not have any factor till square root of n, okay, then it is a prime number. So what is the number that we are talking about? So the current value of n in the loop is 11. Okay, and what is the value of square root of n? Okay, so at this point the square root of n is 3 point something, so let us estimate it to 4. So 4 is greater than root n. Okay, so 4 is greater than root 11. So what we can do at this point, we can exit from the loop, and we will not need all these iterations. Okay, so instead of running the loop till n, we can run the loop till root n, and if at root n there can be only two options of that number. So n can be either a prime number, okay, or it would take a value 1. Okay, if it is perfectly divisible, if we have seen all the factors, this would be 1, or it would be a prime number, because if a number does not have any other factors till square root n, then it is a prime number. Okay, so in this particular iteration, the value of n is 11, the value of root n is 3 point something, and at 4 we have a condition to exit the loop. Okay, so we will run the loop till this particular point, and we will say, okay, if we don't find a divisor till I equal to 3, and as soon as I becomes 4, we will try to exit the loop. So using these two approaches, we are able to come up with a optimized solution. So what we will do, we'll copy this code. Okay, and what we will do is, instead of running the code till n, I will run the code till root n, and here I will say this is fine. And if I now come out of the loop, if you come out of the loop and you check if the value of n is not equal to 1, okay, then that number itself, this number itself is a prime number and is a prime factor of the given number. Okay, so given number is 99, so 11 is a prime factor of 99. So I can just see out that number, that is n. Okay, and the power of that is nothing but what? It is 1. Okay, and it is going to have a single power. So yes, that's it. And now if I run the code, for a given input, we will see the prime factorization. Okay, so let me show it to you. If I say prime factorization, I need to build the code. We have built. Okay, we got one error. Okay, redefinition. So factorize optimized, optimized. If I give the number 99, I get, okay, 3 square into 11 raised to the power 1. If I give the number 72, I still get the same factors. If I give 50, I get the same factors. Okay, so that means our code is working perfectly fine. And this is the root n based approach. So the complexity of this approach would be order of square root of n, and it is better than the previous approach. Okay, so that's all for this video. Hi, so in this lecture we'll discuss prime factorization using sieve that we have already discussed, the sieve to compute primes. So now, when is this method useful? Suppose you have a lot of queries, you want to generate prime factors for q queries. Maybe you want to get the factors of 10, 100, 58, 62. Okay, so you have a lot of queries and you want to efficiently compute factors of a lot of numbers. Okay, so the largest number can be of the order 10 power 7. So let's see how we can use a pre-computed sieve to find out the factors. So what we will do, we'll construct an array like this one, like we did in the prime sieve as well. So we'll start from 2 and we will go to all multiples of 2. Okay, we'll go to all multiples of 2 starting from the number 2 itself. And what we will store, we'll store 2 there. Okay, so instead of marking the multiples of 2, now what we are going to store, we are going to store the smallest possible prime factor of that particular number. So 2 has a multiple 4, so we store a 2 here. It has a multiple 6, we store a 2, 8, 10, 12, 14, 16, 18, 20 and 22. Okay, so next what we go to, we go to 3 and we do the same work. So 3 has so we are going to go on multiples of 3 and we are going to store 3 there. Okay, so we'll go to 6, but 6 at 6 we have already stored the smallest prime factor, so we will not update 6. Okay, we'll go to 9, we'll go to 12, 12 already has, we'll go to 15 and then we'll go to, let's say, 18 and we'll go to 21. Okay, so next what we will do, we'll go to 5. So for 5 we have put 5 here. Then we'll go to 10, 15, 20. All of them are already booked. And we have also discussed that for any number n, like a number like 5, we'll start marking the multiples from n square. Okay, or I square if the number is I. This we have already discussed, because all other numbers which are less than I square, they already have been marked by some other multiple. Okay, so we go to 7. 7 itself is a prime number, we store 7 here. Then for 7 we will see it is going to be at 41. Okay, or 49. Then we go to 11. 11 is a prime number, so it will start marking from 121. Okay, so we put 11 here. And then we go to 13, we put a 13 here. We go to 17, we put a 17 here. We go to 19 and we put a 19 here. Okay, because these are the prime numbers which are left and they will not have any other number which is going to mark them, so they will mark them by default. Okay, so we went to 2, we went to 3, we went to 5, we went to 11 and also 7, and we went to 13, we went to 17 and we went to 19. Okay, and so these numbers themselves are prime numbers. Okay, they are not going to mark themselves. So now once we do this, okay, so this is nothing but the sieve approach that we have already done. Instead of marking true and false, what we are doing is we are storing the smallest prime divisor. Okay, we are storing the smallest prime divisor at every index. Okay, at every index I. We are storing the smallest prime divisor of I at every index. Now you may ask, okay, how do we get the prime factors of a particular number? Okay, we have not seen how to get the prime factors. So it is very easy. So once we are given a number, for example, we are given the number 20. So we will see what is there at 20. Okay, so at 20 we see the number that is there, it is 2. So we divide 20 by 2. We write it as 2 into what? 10. Okay, so we come to 10. At 10 we see what is the divisor of 10. We see it is nothing but 2, and 10 divided by 2 is what? 5. So we go to 5. Okay, at 5 we see what is there. 5 is nothing but it is 5 divided by itself into 1. So once we get 1 we will stop. Okay, so it is nothing but 2 into 2 into 5. Okay, let us talk about a number which is 15. So at 15 the divisor is 3, so we say okay, we'll divide it by 3. So we have 3 as one divisor. 15 divided by 3 leaves us with 5, and we come to 5. We see okay, what is at 5? It is 5, so we put divisor as 5 and we reduce it by 5, we get 1. So once we get 1 we will stop. So this is the approach that you will follow to find divisors of any number. Okay, so this is going to be pretty efficient. So in order to pre-compute this sieve, it is going to take order of n log of n time, same as the prime sieve. And in order to answer a query, okay, in order to answer a query, this time would be even lesser. Okay, so this step in which we are reducing the number to 1, this step is going to work in logarithmic time. So it is going to be log of n for every query. So we have reduced our time complexity from order of n to square root of n, and using prime sieve with pre-computation. Okay, if we ignore the time for pre-computation, we can reduce the time for every query to log of n. Okay, and hence for q queries it is going to take q into log of n time plus n into log of n time for doing the pre-computation. So this is the complexity of this approach. I hope you really understood this approach, and in the next video we'll implement this approach. Hi everyone, in this section we will talk about segmented sieve, and what we will do is we will first understand why do we need a different sieve algorithm when we already have one. Okay, so for that we need to go through a problem statement on Spoj, and this is the question. So it says Peter wants to generate some prime numbers for his crypto systems. Your task is to generate all primes between two given numbers. Okay, for example, you're given a number m, and which is, let's say 10, let's say n is 20, so you want to generate all prime numbers in the range 11, in this range, that is 11, 13, 15, 17 and 19. Okay, so you can easily do it using prime sieve, but the question changes when the constraints are different. Okay, if you look at this value of m and n, the range is very large. Okay, it is of the order 10 power 9, and there is another condition given that the difference in the values of n and m, this would be of the order 10 power 5. So this is 10 power 9 and this is 10 power 5. Effectively, in the worst case, if n can get a value of this order 10 power 9, the value of m would be of the 10 power 9 minus 10 power 5. Okay, so basically the number of elements in any query, this delta would be of the order 10 power 5, but the value of n itself is large. Okay, now you may ask why we cannot use a standard prime sieve to do it. The reason being, in standard prime sieve algorithm, you construct a sieve of size n, and n is of the order 10 power 9. So this would easily take how much memory? It will take, one integer takes how many bytes? It takes 4 bytes, and you have 10 power 9 integers. Okay, so it is going to take 4 into 10 power 9 bytes. And by default, if you want to create an array inside a program, so the standard limit for an array size is of the order 10 power 7. Okay, that means it will take how much memory? 4 into 10 power 7 bytes, which is equal to 40 megabytes of memory. Okay, and now this is roughly 100 times higher. Okay, this is 100 times of this standard limit, so it will be 40 into like 100, it would be 4000 megabytes, which is of the order 4 GB. Okay, so in order to construct this array, you would require 4 GB of RAM, and this RAM will not be available in your system. Okay, because of memory constraints. Okay, if you're running it on a laptop, then 4 GB RAM for this array you will never get. Okay, and in Spoj also you see there is a memory limit given for the problem. So it is given, okay, you can take 1536 MB, which is roughly 1.5 GB, which is the memory limit given for this question. Hence you cannot solve this problem using the standard sieve. So we need something different, and that is where segmented sieve comes into picture, and we will discuss segmented sieve algorithm in the next video. Hi, so you have understood why do we need a different algorithm, which we are calling as segmented sieve. So what we are going to do, we are going to find all prime numbers in this range n to m, and we are given that n to m is of the order 10 power 5. Now let us discuss how we can build this algorithm. Okay, so how we can build the segmented sieve algorithm. So in this algorithm, what we are going to do, first we know that we want to compute the prime numbers in the range n to m. Okay, so we are going to create a separate array. Let's say this array would start from m and it would end at n, but you also know the indexing is zero based. Okay, the indexing in the array is zero based. So in order to represent m, so we will move it by m steps behind. We will say, okay, we will map it with index 0. So effectively you would be doing m minus m. Okay, this index is m plus 1, so it would be at 1, it would be at 2, and so on. And finally the last element would be at n minus, it would be like the n minus mth index. So effectively you have done shifting, basically we will say, okay, this is nothing but 0. So we will represent the numbers from the range m to n by the range 0 to n minus m. Okay, this is one thing. And what we have learned is, let's also talk about regular prime sieve. Okay, let's talk about regular prime sieve. So we have numbers in this range and we want to mark all the numbers which are not prime, okay. And we have also learned, in order to mark if a number is prime or not, what we generally do is we find one divisor of that number which is less than root n. Okay, which is less than or equal to root of that number. Okay, this is what we have done. If you find at least one divisor of that number which is less than or equal to root n, we say the given number is not prime. Now what we want is, we want to find the divisors of the numbers in the range m to n, and these divisors, okay, I need at least one divisor. Okay, so if I get at least one divisor which is less than root n, that means I can easily say that the given number is not prime. Okay, so what I'm going to do, so now the maximum number is n. This is given in the question. Maximum range could be n. So what we are going to do, using prime sieve, we are going to find all primes up to root n. For example, let's say if n is 100, okay, so what we will do, we'll create a segmented sieve which will contain all divisors up to 10, all primes up to 10. So that sieve will contain 2, 3, 5 and 7. Okay, so this would be your sieve array. So this is going to store all primes up to root n. Okay, all primes up to root n. Now you may ask, how do we construct this? You can construct this using the standard prime sieve algorithm that we have learned, that you first put all the numbers like 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you say, okay, I will mark multiples of 2. So you say, okay, 4 is gone, 6 is gone, 8 is gone, 10 is gone. Then you mark multiples of 3 starting from 3 square. So 3 square is 9. Then you start from 5. So and so on. So finally you're left with the numbers 2, 3, 5, 7, which are stored inside, let's say, another data structure, which is an array or a vector. So once you have these numbers, what you can do is, you can pick 2 and you can mark all multiples of let's say you can mark all multiples of 2 which are in this range as not prime. So maybe you mark this one, this one, this one, this one, this one. Then you pick 3 and you mark some of the numbers which are multiples of 3 and which lie in this particular range as not prime. Maybe you mark this one, okay? Then you mark some multiples of 5 starting from 5 square, and so on, okay, which are lying in this range. Maybe you mark this one. So finally you mark multiples of 7, and finally whatever is left, that would be a prime number, okay? So it is effectively, we are doing nothing but we are saying, okay, for all the numbers which are in the range m to n, we will try to find at least one divisor of that number which is less than equal to root of that particular number. If you get at least one divisor, then that number would be marked as not prime, and finally whatever is left, they all would be prime number, okay? So whatever is left inside a circle, they would be a prime number. So you get, okay, this is a prime number, this is a prime number, okay? Now the question is how we are going to implement it, okay? So what we are going to do, we are not going to construct this primes array for every test case, okay? So we are going to construct this only once. That means this would be pre-computed for the largest value of n, okay? So you pre-compute it for the largest value of n. So the largest value of n in the question is 10 power 9, okay? So that means up to n, that is roughly of the order root of n. So it is greater than 10 power 4, less than 10 power 5. So let's approximate it as 10 power 5. So I will compute all primes up to 10 power 5 and store them inside a vector. And using that vector, whatever query I get, whatever query from m to n I get, I construct an array of this particular size, and I say, okay, what I'm going to do, I'm going to iterate over the prime numbers, and I'm going to mark the numbers inside this segment. So we call this array as segment, and we call this array as primes. So we will iterate over the primes, and we will mark the numbers in the segment which are multiples of that prime number as not prime, okay, as not prime. So finally whatever we are left in the segment would be a prime number. So this is a very simple idea. The only thing is, this method has brought down the requirements of using a very large memory, okay? Here we are using two arrays. So this array would be of the size at max 10 power 5. This array, primes array, would be of the max of the size, how much? 10 power 5, okay? And this primes would be even lesser than that. So effectively, by using up to 2 into 10 power 5 memory, we should be able to solve this question. 2 into 10 power 5 into 4 bytes, okay? That is much lesser, okay? That's not even 1 MB. So we can easily solve this problem, and that's what we are going to do. So let's see the implementation of segmented sieve in the next video. Hi everyone, in this lecture we'll be talking about the code for segmented sieve. So let's see what we have learned so far. So first of all, we discussed that we will actually need two sieves, okay? So two arrays. So one array will contain primes up to 10 power 5, because we discussed in the segment that we are figuring out, the range is up to 10 power 9, okay? So we need to find out all the prime numbers that are up to 10 power 5 or less than 10 power 5, so that we can mark the multiples of the primes as non-prime in this array. So we'll create two arrays. One is a segment array, and one would be an array of primes, okay? So what we can do, we can generate this using the normal sieve that we have discussed, okay? And we can iterate over the normal sieve, and we can store the numbers inside a vector called primes, okay? So we'll generate a vector of primes, so that when we are iterating, we don't waste our time iterating over numbers which are not prime. We will store only the prime numbers inside this particular vector, and this we are going to generate using the sieve method. So I have taken n as 10 power 5. All right, so what we will do, we'll generate the normal sieve, and for the normal sieve I need a sieve array, okay? So everything is initially set to 0, and then I say, okay, I also have a vector of primes, and this vector we will use in the segmented sieve algorithm. Let's see how we can construct the normal sieve. So I can say for long I equal to 2, I less than equal to n, I plus plus, if I say, okay, if sieve of I, if this is 0, then it is a prime number. So what I can do, I can say primes dot push back I, and we are going to mark the multiples of I as non-prime. So I can say for long j, that is equal to I into I. We discussed multiples of any prime number start from I square, because all multiples which are less than I square, they are already marked by some other number which is less than I. So j plus equals to I. So what we do, we say, okay, sieve array of j is 1, so that means that number is not prime. Okay, so now what is going to happen after this loop, we will have this vector of primes, because we are pushing everything inside this vector. So we are going to generate this array only once, and this would be shared across all the test cases, but this segment would be created for each test case separately. So what we have done, we've generated a vector of primes using the normal sieve method. Okay, and I hope you are able to understand this one. From here we will write the code for main, and in that we will also implement the segmented sieve. In the question, first we will pre-compute all the primes by calling the sieve method, and once it is done, what we are going to do, we are going to take input the test cases. So I can say int t seam t, and we'll take input the values of n and m for every test case. So int mn, and I can say scene m and n. Okay, so let's say m is something this point and n is this point. So we want to find out the primes in this particular range. So we discussed that we will also do shifting, and what will happen due to shifting is this m will come to index 0 and n will come to index n minus 1. So effectively in the actual array, this would be mapped to index 0 and this would be mapped to n minus m. So what we did, we subtracted m, so we shifted everything by m positions. Okay, what should be the size of this array? So the size of this array should be n minus m plus 1. Why? Because the last index is n minus m, so that means the total size would be 1 greater than the last index. So we'll say, okay, we are creating a vector of integers, we call it as segment, and the size is n minus m plus 1, and everything is set to 0. Okay, now what we can do, we will say, okay, in this segment, let's say the numbers are from 99 to, let's say 150. So what we will do, we will go through these numbers and we will mark the nearest multiple of that number in this segment. We'll start from the nearest multiple of 99. So earlier in the normal sieve algorithm, given 2, you start marking from 2 square, that is 4. Given 3, you start marking from 9. But here, given a prime number 2, you will find the nearest multiple of 2 in this array, that would be nothing but 100 or 98. You'll start marking from that, and that's how we are going to do. So I can say I will iterate over the primes vector, and let's see how we can write this loop. For auto some number prime p which is in the primes array, so let's say p is 2 or p is 3. So what we are going to do, we are going to say, okay, let us mark the multiples of 2, but only the multiples which lie in this segment as not prime. So one thing to notice, we may have a number like suppose we are done with 2, we are done with 3, we are done with 5, we are done with 7, we are done with 11. Okay, we are at 13. So now the first number that 13 will mark would be 13 square, that is 169, and that clearly is outside the range of this particular vector. So that means we should stop early. We should not iterate over 10 power 5 primes. Stop when prime square becomes greater than your range in the segment. So we can say if p into p is greater than n, we should break the loop. So we have not put the condition here. You can either put the condition here, or you can have an early stopping when this condition is hit. When the square of the prime number is greater than n, that means we are outside the range of segment. Otherwise, what we need to do? Otherwise, we need to find the nearest starting point. So that starting point is it is going to be what? It is going to be the number that is m divided by p, that is prime, into p. So now let me tell you how we are computing this. So let's say the prime is 2, okay, and what is the value of n? The value of m is 99. We are finding out what is the multiple of 2 that is close to 99, okay. So that multiple is nothing but 99 divided by 2 into 2. So this will give us 49 into 2, that is 98. So obviously either we get a multiple which is just lesser, or we get a multiple which is just higher. We actually get this number which is just one box behind the actual number. So what we can do, we can actually start marking the numbers from here, okay. Start marking the numbers as not prime from start, but if the start lies outside the boundary, we will jump to the next position, okay. So we can say for int j equal to start, okay, j less than equal to n, j equal to j plus that prime number. So we are going to take a jump of 2. So for example, we have 98, we have 100, we have 102. So every time we are going to mark the multiples, we'll be taking the jump of prime. But now 98 is outside, it is less than m, okay. So what I can say, if somehow the value of j is less than m, then we will simply say continue, because the index 98 does not exist in the array, and we will continue, okay. Otherwise, if it is not the case, we will say segment of j, but now the actual index is not j, it is j minus m, okay. So if you are saying the index is j, or the value is j in this segment, so in the actual array it is j minus m. So I can say segment of j minus m, this should be equal to 1. So we marked it as not prime. So we marked it as not prime, okay. Now there is one special case that we have not seen yet, okay. So once we are done, after this for loop, we will have all the primes stored as 0 in the segment array. That means they will remain unmarked, okay. So we'll find out those primes, but there is one special case that we have to handle, okay. Now we have only discussed the case when, let's say, we have a range of numbers. Let's say we have primes stored as 1, 2, 3, 5, 7, 11, 13 and so on, okay. So up to 10 power 5 we have all the primes. This is your sieve array or the primes array. So, and we have a segment in which we are working on. Let's say this segment starts from a range m equal to 10 and it goes till n equal to 100. Now clearly there is an overlap. Okay. So not one. So you can see 10, 11, 12, 13, 14. These are the numbers that we are talking about. So clearly there is a overlap between the primes array and this array. And what may happen is, when you choose a starting point, for example, you say, okay, tell me the starting point for the prime 7, okay. So what we will get as a starting point, so start is m upon p, so that is 10 divided by p is nothing but 7 into p, so this is nothing but 1 into 7, that is equal to 7. So we'll say for 7 we are going to mark the first number, which is 7, okay. So this clearly lies outside the range of m, which is fine. This is not an issue. Let me take a different example. Let's say for a value of m which is less than p, this is a case. For example, if your m is if your prime is 13, okay, and let's say this range is up to 500, so this condition is not true. P square is not greater than n. So what will happen? You will say, okay, I will calculate the starting point as m upon p. So what is m? M is 10. What is the prime number? The prime number is larger than m into the prime number. This number would become 0 in some cases when the value of m is smaller than the prime number. Okay, so 10 by 13 is 0 into 13 is 0. So you will say, okay, for 13 I'm going to mark the numbers from 0th index, which will make your code inefficient, because although we have this condition, if j is less than m, continue, but ideally what we should be doing is, for 13 the first multiple that we can say, okay, that we should be marking, it should be like 2 into 13. At least we should start from 26, not from 0, but we should start from 26. So in order to save some iterations, we can say, okay, if your prime number is greater than equal to m, okay, and this prime number is less than equal to n. So if the prime number itself lies in the range of segmented sieve, then the starting point should be 2 into that prime, not this start. Okay, so this is one more condition. So it's again kind of a special case. I've shown it to you. This you need to handle. So once we are done, we can say, okay, for int I equal to m, I less than equal to n, I plus plus, we can check if segment of I minus m is 0 and the value of I should not be equal to 1. Okay, 1 is not prime. So I can just see out I followed by endl. All right, and we also need to give a endl here for each test case. So that should be, so let me see the brackets. Okay, so we have this while loop. All right, so we are done with the while loop. Now this part we are doing for every test case, this part we are doing for every test case, and sieve we are building a common sieve for all the inputs. So let's open up terminal and see. So we have one error, sieve of I. So this array should be renamed as sieve. Oh, but that clashes with the name. So let me just say sieve array, and the code is building fine. So let's test our code for few examples. Let's say we have 3 test cases. Give us all the primes in 2 to 10. It is working fine. Give us all the primes in 200 to 250. So it is looks fine. Give us all the primes between, let's say, 90 to 100. So we have only one prime, 97. And we also submitted this code on Spoj and it works perfectly fine.